Next up, we're going to talk about arithmetic and logical operations. These are operations that are implemented by the ALU, or the arithmetic and logical unit. So the standard format of an ALU instruction is an opcode, a function, and 2 registers. So let's start with the notation that we use to describe the ALU operations. We're going to specify 2 registers, RA and RB. And the semantics of the instruction are that we're going to take RB, i.e. the value in the register file corresponding to the register RB, apply the function that we're doing to another operand, RA, and we're going to take that result and put it in RB. Taking that and making it a little more concrete, if we wanted to do an add, we might say add Q, register R8 into R9. And so that says that we're going to take the sum of R8 and R9 and put it into R9. With addition, the order of registers doesn't matter. But when we start to look at subtraction, notice that if we still say sub R8, R9, that translates into R9 minus R8, take the result and put that into R9. Okay, so that's what these mean logically. Now, how do we encode them? All the ALU operations are going to have an opcode of 6, and then they're going to have a specific value to correspond to the function. So for example, our add instruction is function 0. Subtract is function 1, and is function 2, and XOR is function 3. Now, turns out that the 313 version of our simulator has some bonus instructions. So function 4 is going to allow you to multiply, 5 is division, and 6 is modulo. Like subtraction, the order of the operands for division and modulo really matters, right? So if you say div q R8, R9, what that says is you take R9, you divide it by R8, and you put the result into R9. Now there's another interesting feature of the ALU operations, and that is that they set the condition codes. So you might remember when we introduced all the visible state, we mentioned that there were these condition codes, and in particular, there were these 3 flag values, ZF, SF, and OF. Where ZF corresponds to the 0 flag, which is set if the last ALU operation produced a 0. Similarly, SF is a sign bit, and that is set if the last operation produced a negative number, which we interpret as a number that sets the high order bit to be 1. And then finally, there's the overflow bit, which indicates that the last arithmetic operation produced a 2's complement overflow. If that doesn't make sense, hold tight. I'm going to actually run through some code in the simulator to demonstrate both the ALU operations at work and also how you produce an overflow. So here's the program that we're going to be working with. And rather than walk through it here, what I'd like to do is switch us over to the simulator where we'll load it in and then we can actually watch it run. So let's take a look at our friend, the CS313 simulator. Just like before, we have all the registers here, but now I want to draw your attention to the condition codes down here. And as we execute, you'll see when they get set. So if you see the dashes, that means that they're all 0s. And as we execute instructions and those bits get set, they'll pop up. So let's begin. We're going to start by loading RAX and RBX with some constant values. So let's run 1 cycle at a time. And now you should see that RAX and RBX have the numbers 1 and 2 respectively. Next, what we're going to do is we're going to add them together. And I hope everyone agrees that we should end up with a 3. And the 3 is an RBX because we did an add of RAX into RBX. So now that RBX is 3, let's try doing a subtraction. So what that says is we're going to take the value in RBX, which is 3, subtract RAX, which is 1, and that should give us a 2. And sure enough, we get the 2. Now, let's see what happens if we subtract RBX from RAX. So RBX is 2, RAX is 1. We'd better get a -1. So let's run a cycle. And sure enough, RAX is full of F's, which is the 2's complement representation of -1. And notice that down here on the condition codes, our sign bit is set, indicating that the prior instruction produced a number whose value is less than 0. Next, I'm going to do a logical operation. I'm going to take the contents of RAX and I'm going to XOR it with RAX. Now recall what XOR does, is it says if the bits have the same value, that's a 0, and if they have a different value, then it's a 1. So when I XOR a register with itself, I set the register to 0, because every place that the bits are the same turns into a 0. Also, because I just turned that register into a 0, our Z bit gets set, indicating that the last operation produced a 0. If I repeat the exact same operation and do an XOR, I'll get the exact same result. I still have a 0, and I still have the Z bit set. Let's play around some more. Now that I have a 0 in RAX, let's subtract RBX from it. You might recall, and you can see that RBX is 2. So I would expect that I'm going to get a -2. And sure enough, we get FFFFF, blah, 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 E, which corresponds to -2. And because it's -2, the S bit is set. Let's try the other logical operation, AND Q. If I take the contents of RAX and I AND it with itself, what happens? Well, an AND says only put a 1 if both bits are a 1. So that's going to preserve the value in RAX. And since that value was negative, it's still negative, and the S bit is set. Next, let's see what happens when I add the value in RAX, -2, to the value in RBX, which was +2. I hope we get a 0. Oops, nope, that isn't what I did. Wait a minute. We did an add of -2. I'm sorry, I did an add of RAX and RAX, not RAX and RBX. And sure enough, we got a -4 and the sign bit set. My bad. Our next instruction is now going to add RAX into RBX. So RAX is a -4, RBX is 2, and so if I add -4 into 2, I'd better get a -2. So run one cycle, and sure enough, our 2 has changed to a -2. That's a negative result. Our sign bit is set. Now, if I add these two numbers together, I'm adding two negative numbers. We would hope that we get another negative number, in particular -6, and that our sign bit stays set. And sure enough, that's what happens. Next, let's move a 1 into RAX. And now what are we going to do? Well, we're going to add the contents of RBX, which you might recall is -2, into RAX. So what happens? We go back to having a -1 because we took +1, added -2, that gives us a -1. Next up, we're going to put the constant 3 into RAX so that we can now add RAX and RBX. And we're going to put the result in RBX. So we had a -2 here. We have a +3 here. We're going to run one cycle, and we get a 1 here. You'll notice the comment here is incorrect because I actually changed the program after I wrote the comments, and I didn't go back and change the comment, which is a bad thing to do. So in the video, you'll see that that comment is wrong, but I will very carefully go back and fix the code so that if you play with the code, the comment will be correct. Let's wrap up by generating an overflow. I'm going to load register RAX with the largest positive number I can represent. So I leave a 0 in the high order bit, i.e. the 8-bit isn't set, and I set everything else to 1. And what I'm going to do is I'm going to add the back to itself. What that's going to do is force a bit into that high order, which suddenly took two positive numbers, added them together, and produced a negative. And ideally, that should set our overflow bit and turn the sign bit. So I hope that this is both giving you a little bit more practice with the simulator and also walked you through how those condition codes change as we do different operations. Now you might wonder, why do we care about the condition codes? And what you'll see in the next video is that we have instructions that use those condition codes to change how our program behaves.